called Lucy. Okay, Lucy in English movie. It's a fictional kind of thing we can say, but they have like one scene in that movie explains about the time. So I just want to play it for 2 minutes so that everyone can get some deeper understanding. So there is no intention of playing movie here, but I think that will depict much better about the time. The scene will depict much more about the time. Can you hear the audio, Ganesh?
So it's a bit low, like a lot low, you can't hear.
Okay, you can't hear. Okay, let me play it.
It's not audible, so.
Okay, it was audible, I hope. So you have seen this nice scene where she explains that time is the only measure. Without time, nothing exists. Is that clear? Was it audible, Ganesh?
No, sir. No, sir, it was kind of muted.
It wasn't audible.
No, sir.
Okay, that's when I'll post this. I'll crop and post this particular video scene. Then you can watch it again and again. I don't know. It was supposed to be audible. Fine, that's it. The conclusion is that nothing exists without time. Time is the only measure. So that's what the conclusion was. So to start with, unit two, we have some basic definitions. Some basic definitions today to understand, which we already have done. But let me revise it once again. So these are the standard signals which we need to understand before proceeding with unit 2. So the first one is impulse function. Impulse function, you might have already started this in signals and system. So the representation of impulse is given as uh, del of t, which has a value of unity only at t equal to 0, time equal to 0. So if you draw this graphical representation for the impulse function on a time scale, so time 0 second, 1 second, 2 second, 3 second. So at 0th second only it will have its magnitude equal to 1, and we assume or we interpret that it has a very less width and a very high length on the magnitude scale. So this is the representation of impulse function. So many of you might have got a confusion, like it's usual common that how we can have a signal at t equal to 0 second, or how we can generate a signal at t equal to 0 second, and for rest of the time how we can make that signal to be equal to 0. So all such confusions will run around in your mind. So just understand the philosophical meaning of this impulse function. So impulse function is a nothing but giving a sudden input for shorter duration of time. That's what the simplest meaning of impulse function is. Giving a sudden input for a shorter duration of time and understanding how a system behaves. So for example, I had said on example, like if you just push and remove your finger, okay, while moving a mass block, that can be assumed as an impulse function. Or best example I often give so that you can remember for longer time is that slap your friend and know how he behaves. That is called an impulse input, and the behavior or the response is called impulse response. So don't get confused on all the time scale and magnitude scale. Just understand the meaning of impulse function in that way. I hope it is clear. And this standard signal, like where it is applicable, where it is applied, all those again questions will arise. But it is actually a test signal. It can be categorized as a test signal also. So standard signals are also called as test signal. Often we use to test our designs. That's it. Okay. So there is no particular application wherein which we have to generate our signal and then only it will work. No, it's not like that way of interpretation. It is just for a test signal, testing scenario. So obviously when we come for practical testing, this definition of impulse will change. So, okay, it depends on your application. So you may have a little larger magnitude and a little more of width, depending on the application you want to test. But when we go for a theoretical analysis or a simulation in software, we define impulse like this. That's it. Okay, next second one is step function. So step function is already known. So u of t equal to k, magnitude equal to k, some constant for t equal to or greater than 0. So the signal starts from t equal to 0 with a magnitude of k. Then for rest all t, I mean for t lesser than 0, there doesn't exist any signal at all. Okay. So again a confusion may arise, like how you can make a signal equal to 0 for t lesser than 0 seconds. So what does that mean? How we can generate such type of signals where it is applicable? So for all these questions, the answer is it is a convention that as soon as you switch on a DC battery, which resembles the output same as a step function, okay. So as soon as you switch on the battery, DC battery, you can start counting your time as t equal to 0 seconds. That's it. So that's how you can interpret. Next, the ramp function. So the ramp function is given by k multiplied by time t. Kt for t equal to or greater than 0, and again it is 0 for t less than or 0. So the representation goes like this, and the graphical representation is like this. It's very simple. Everyone can understand this. So if you make two columns, one for t and another for r of t, which is equal to kt, so you go on increasing the time scale from 0, 1, 2, 3, 4. Then you parallelly calculate the values of kt, you will get this kind of graph. Okay. So I hope I am able to reach everyone about the concepts of the standard signals or test signals. And coming to the Laplace transform of this, these are some standard functions in which the Laplace transform is directly available, or you can even calculate on your own using the basic formula, which you have studied in mathematics or you will be studying in signals and system. So the Laplace transform for a impulse function is 1, which we write it as del of s equal to 1. Then the Laplace transform for a step function is 1 by s. So if there is a constant k, it will become k by s. So similarly for the ramp function, we have k by s square. So I want every diploma students to solve this, or at least go through the solution now, finding the Laplace transform for these functions. You can directly Google it. Laplace for step and Laplace for ramp. So this is out of scope for us, so I'm not solving anything here. Fine. So any doubts, clarification here? Any kind of doubt. So think parallelly about the practical aspect of whatever I teach here. Then only the control system is useful. Then only the live class is useful. So if you create your doubts, you are free to ask. So one may have a question just in general. I'm trying to reach everyone in the class. So one may have a question, can we have a signal for t lesser than 0? Okay, can we have a finite signal for t lesser than 0? Any kind of signal other than this or including this. Can anyone answer me? If you look into the perspective of practical application, can we have a finite signal for t lesser than 0? So my answer is of course you can have it. You can have it. But our convention is we start measuring from particular point of time. So that's why I will say that particular point of time as with reference to 0 seconds. Fine. So when I say 0 seconds, this is how your step function starts. So that is the meaning. Fine. Suppose imagine you have two batteries, one of 5 volt and one of 10 volt, connected to say some resistive circuit. And the first in the first case, I will switch on the 5 volt battery. So a 5 volt signal is applied. So after say some time, 10 seconds, I will switch on the 10 volt battery also. Okay. So it depends on your convention that which one you take as 0 seconds. You can take the switching on of 5 volt as 0 seconds, which is switched on first, or you can take the switching on of 10 volt battery as the starting time t equal to 0 seconds. Okay, so then it means the first battery was switched on earlier to the second battery, 10 volt battery. So it means you are taking the 0 second reference for the second battery. So that means there exists some signal even for t lesser than 0. Okay, even t lesser than 0. So in general, it depends on our convention of taking the time scale. Fine, I hope I'm clear. Next, take down some definitions. I feel, please, everyone, please write these points. Okay, when I share the slides, maintain this in your notes. Next, definitions, some basic definitions. Order of a system. So the highest power of S in the denominator of transfer function is called as order of the system. I repeat, the simple definition, highest power of S in the denominator, polynomial you can say, or just denominator is fine, of the transfer function is called order of the system. Please note this also, we need it often. So when I write the transfer function as 1 divided by s plus 1, 1 divided by s plus 1, obviously the power of s here is 1, s raised to 1. So this is called order 1 system or first order system. Similarly, we have s square plus 2 or 1 divided by s square plus 2s plus 2. So if I look at the highest power of s in this polynomial of the denominator, the order is 2 and the system is called as second order system. So similarly, other example, if you have say this type of polynomial, okay, in the denominator, you have to multiply all the terms inside bracket and look for the highest order of s. So one can directly say that you can at max have 3 as the highest. Okay, 3 as the highest power. So therefore it is third order system. Third order system. Okay, one small announcement I received just now. CI1 is from 16th, 17th and 19th October. I repeat, CI1 dates are 16th, 17th and 19th October. It will be descriptive and students must submit the original answer sheet. Okay, must submit the original answer sheets once the offline classes starts. Okay, once the offline classes starts. So it will be descriptive and students must submit the original answer sheets once the offline classes start. So this is the message what I received. Okay, we can interpret it in our own way. I'll continue with the class. Next, another definition, characteristic equation. Please note this down, this particular definition, characteristic equation. The denominator polynomial of overall transfer function is called as characteristic equation. Okay, the denominator polynomial of overall transfer function is called as characteristic equation. So please remember this. Fine. So it's very simple. Huh? There's nothing much I have to explain. I have given one example also. Next, the other definition is poles and zeros of a system. Poles and zeros of a system. So poles are nothing but the roots of denominator polynomial. So you have a polynomial in the denominator, and if you find the roots of that polynomial, it is called as poles of the system. So poles of the system are also called as characteristic roots. So why it is called as characteristic roots? Because we already know denominator polynomial is termed as characteristic equation. Okay. The roots of characteristic equation are nothing but roots of the denominator polynomial. So we have another terminology for it. The poles are also called as characteristic roots. Just note it down, guys. Frequently we use it. Then what is zeros of the system? So zeros of the system is in the other way. It is roots of numerator polynomial of the overall system transfer function. Fine. So the roots of numerator polynomial are called as zeros. Roots of the denominator polynomial are called as poles or characteristic roots. So these two definitions have means quite different. News ಏನು? Oh. Just 1 second, hold on, please. Hello, sorry for the interruption. Okay, we were studying about the poles and zeros. So before proceeding, I request everyone to follow the guidelines to avoid spread of corona. Please do not ignore. I repeat, and if it is not necessary, please don't go out. Okay, that's fine. Here I have given one example. G of s equal to s plus 1, s plus 2 divided by s plus 3 and s plus 4. Here I will term it as overall transfer function or system transfer function. Okay. So as I have said, plant transfer function and system transfer functions are different. So system transfer function is including all the closed loops. Okay. And plant transfer function is only with respect to that particular plant. And we often refer in our syllabus as only the system transfer function. Fine. So here, if you look at these polynomials, if you multiply, you will get s square plus 3s plus 2. Then denominator polynomial is s square plus 7s plus 12. Okay. So finding the roots of these two polynomials is very easy. So if you look at the numerator polynomial, the roots are nothing but -1 and -2. Okay. So if you substitute -1, this polynomial will become 0. Substitute -2, this polynomial becomes 0. So roots are found by equating these polynomials equal to 0. Okay. Separately equating to 0. Then similarly denominator is having -3 and -4 as the roots. Therefore we call poles of this polynomial or this polynomial as -3 and -4. And zeros of this polynomial as -1 and -2. Fine. Now it is very simple that the number of poles depend on order of the system. So if you have say 4 order system, obviously there will be 4 poles. Okay. So now another scenario is these poles can be real. Okay, these poles can be real or complex or pure imaginary. So anything is possible. There is no restriction on the type that these zeros or poles can be. Fine. So this is just a mathematical foundation required for the next part. Next, the standard input that we are considering, I mean that in general is considered while studying the time domain analysis of a system is a step function. Is a step function, and specifically we use unit step input. We use unit step input to study the time domain analysis. So what I meant to say, a designer wants to know the behavior of a system. If a designer wants to know the behavior of the system, we give him certain specifications, and those specifications are always with respect to unit step function. Okay. So the test signal or standard input signal we use is unit step function. That is, if you have a system transfer function as g of s, and if r of s is input, c of s is output, our r of t, the inverse of r of s, which is r of t, is defined as r of t equal to unity for t greater than or equal to 0 and 0 for t less than 0. So on the conventional time scale, we apply a signal whose magnitude is unity. That is unit step input function. The other way of writing r of t is u of t. Okay, the magnitude into u of t. So we see this u of t is also will also represent by default a unit step function u of t. So you use this oftenly in signals and systems. So our input r of t is u of t, and its Laplace is 1 by s. Right. So that's it about today's class, and I still have some material to share, but I don't know. I cannot continue. So just take down the heading for the next class, and we will start time domain analysis of first order system. Time domain analysis of first order system, and we start this in the next class. So before starting the next class, please go through all this material which I will upload in the drives. So whether the videos are useful, whichever I have uploaded in the drives, anybody is making use of it?
So in first unit, DCs are going to come.
Hello, voice is breaking. Can you come again?
So unit 1 DC servo motors are going to come. Like
In
in
the
last year
exam?
paper it was given.
No,
Yeah.
no, no, no. Don't refer last year paper. Your syllabus